Alright, here's the problem with modern machine learning. The better you are at evaluating how well you're performing on some particular task you're doing right now, the easier it will be to figure out what you need to do in order to perform well. For example, let's consider a video game. Imagine you're in some three-dimensional game world and run around in first person. Now, the game designers for this game were completely terrible, so when you run around, you see spheres and cubes, and you can collect them by running over them. But there is no indication whatsoever. Nothing changes in the game except that the objects disappear. So how should the player know that the cubes are like healing cubes that heal you, replenish your health, while the spheres damage you? If that's how the game works, then certainly the player would have a really hard time figuring this out. Imagine a scenario where you run into a bunch of spheres and then you die at some point because you lose each time 10 HP and you have start with 100. So if you collect 10, then you die, assuming you didn't collect cubes which heal you again. The point of this example is that the game wouldn't provide the player basically with any good feedback. So it's really hard for the player to figure out what they need to do in order to perform well. Let's imagine that the goal of the game is to get to 200 health points, meaning you need to collect 10 cubes and no spheres, or that is the easiest way to win. Depending on what is the frequency of spheres and cubes that are encountered in the environment, it might even look like to the player as if collecting the spheres is good. For example, if there are lots more cubes than spheres and the player always follows the strategy of collecting all of the objects that they see, then they would still win. It is just that it would take them a lot longer because they didn't get this immediate feedback on, was this a good thing that I was doing, that I was collecting this object? And of course, I'm imagining that they don't have any UI that would tell them what is their current HP level. Now we can imagine game B, which is basically the same as game A, but now we have lots of feedback for the player. Each time they collect the cube, they hear some nice rewarding sound. And each time they collect the sphere, they hear some negative sound. Getting this kind of feedback allows the player to develop a policy that will score highly in terms of the game, without really needing to develop a really deep understanding of what is going on. In the case of game A, where we don't get any feedback, the player really needs to experiment and build a good model of what is going on in the environment and how it works in order to even figure out that collecting the spheres is bad and collecting the cubes is good. In game B, it is possible for the player to develop the policy of always collect the cubes and avoid the spheres without really understanding why this is the case, as long as they can perceive the positive sound signal as being something positive and the negative thing as being something negative. In fact, they don't even need to understand the game to the extent that it's about health points and that they need to reach 200 in order to win. So this illustrates that if we have a good feedback mechanism, we can develop a policy that performs well while needing a less well-founded understanding of the underlying mechanisms in the world. And the same is true in general, basically, but specifically it's also true for the case of machine learning research. Right now, we don't really have a good understanding of what are the internal algorithms that, for example, GPT uses in order to be so good at predicting the text. But because we know exactly what it means to be good at predicting the next token in some data set, We can just do some search, like the engineers experimenting with different kinds of architectures, different setups, different hyperparameters. And then we can evaluate for any change that we made, was this now increasing the performance? Did we get better at predicting the next token? And we can do this without having a good understanding of what our system is doing or how it works. Having a better understanding, of course, helps. It allows you to design better things to try out that might increase performance, that are more likely to actually increase the performance. Let's consider the space of all possible models. Every dot represents a specific model, meaning some specific architecture and possibly training procedure and whatever else you use in order to define a particular model. Now, some of these models will be AGIs. They will be really capable. And there will also be any possible agent basically inside of this thing, even things that are completely dumb and wouldn't even be described as agents. Now, let's think of this in terms of we are being in the middle and we are expanding from the middle out our understanding, meaning that the further away from the middle we go, the more difficult to understand the models become. We can visualize the space of all the models that we have a really good grasp on, that we basically completely understand how they work. Now, because of the phenomenon that I was explaining before, there will be a larger set of models that we can get to by just doing some experimentation until we perform really well on some specific task where we know what it means to perform well. And then we can optimize based on the observed performance rather than on understanding the system. The main problem now is that if we just increase our understanding, then you might first think that, oh, now we understand a larger thing of all of the models that we could conceive. So that is really good. Now we have a better understanding overall of all the systems that we get. But this is not the case, because increasing our understanding here has sort of the effect that we also are now able to conceive more of the capable models. That means that the green border, which contains all of the model that we empirically could get to, also expands to include more models. So if we take the green area and divide it by the red area, we get the fraction of the models that we can construct, which we do understand very well how they work. That fraction of models where we understand how well they work out of all of the models we could build is not necessarily increasing if we are increasing our understanding. And this is very problematic. Let's assume one of these dots is a misaligned AGI that would just kill everybody if we just build it. Now, if we were to understand the system very well, if it was inside of the red area, then we would understand that this system is dangerous and that we shouldn't deploy it. However, it's not in this area, instead it is here. It was outside of the first border of the green border of the systems that we could conceive, and increasing our understanding made it such that we could reach further through empirical methodology into the space of capable models, getting a model which is more complicated and more capable, but also now very dangerous, existentially so. Now, this model is somewhat simplified, but to me it seems like this probably describes the reality that we are living in right now. If the current trends continue in deep learning, then we are probably in a situation that is pretty similar to the things I described so far. The model that I described so far is describing what happens just by default by capabilities researchers trying to make their models just more and more capable. They will increase their understanding of the things that they are doing, and then they will be able to reach out further with the empirical methods. However, the same thing is probably applicable to basically any thing that you can do in order to increase your understanding. For example, if we have mechanistic interpretability, then we might use mechanistic interpretability in order to increase the red area, but using insights from mechanistic interpretability, capabilities researchers could use these insights in order to then reach out further into the space of all possible models. Now, it might be that if we do mechanistic interpretability, this red ball is sort of maybe growing faster than if we were just letting the capabilities researchers do whatever they are doing, but it might not really help. Even if this bulb just grows faster, and maybe even if there is some sort of beneficial trade-off, like let's say if a capabilities researcher just does the thing where they try to understand something better, then maybe for each increase, for each doubling in the area of the red blob, we might get 2 doublings in the area of the green blob. And we could imagine that for mechanistic interpretability, for each doubling in the red blob, we would only get multiply the size of the green blob by 3, or potentially even something good like 1.9. But even if we get really good numbers like that, even if we make this red ball of our understanding grow faster than the ball of the things that we can do by using empirical methods where we don't really understand the models, then it might still be pretty dangerous because we're advancing the rate at which we will be in the future able to, basically we get sooner to the point that we will be able to pull out this model in the head, which then kills us. And it would kill us because we are actually that stupid and would pull out this model if we could, because there's just such an enormous economic incentive to do this. And if you can't understand the system very well, it seems quite likely that you won't notice that the system is actually dangerous. And I expect that even if we could sort of filter out some of the systems, if we have some way of knowing roughly what systems, like maybe our understanding is sort of like good enough to say that this model here is too dangerous, we won't deploy it, even if I can't understand it completely why it would be dangerous or what's the exact computation that is maligned. But I expect that there will be other people who will do the kind of dumb thing of using the knowledge of that the particular system here matching to like certain attributes of the system such that we won't get the system out anymore with the training procedure. And they will include lots of attributes like that where we could tell the system is dangerous, but it will be such that this kind of classification of systems that we know are dangerous, which are now like exemplified by drawing these orange circles, maybe we know these systems are dangerous, and we just know but that based on some sort of heuristics, but we don't have a really good understanding of how the systems actually work, then we can still end up with, because we used our understanding of what is dangerous in order to guide our search process over the models in some way, we will actually now select the models that we can't tell are maligned, but they might still be maligned and we might not notice, meaning that we might still pull out this model if we don't understand it well enough and if our heuristics don't generalize to it such that we can't recognize at all that it is dangerous. That I would expect is basically what happens, especially because I think most models are probably maligned. We want to be very careful what kind of model we actually choose, because most of the models are not going to do what we want them to do. It would probably be more accurate if I'm just drawing one blue circle, which is the actual aligned model, whereas all other models are not aligned. And even if we classify 50% correctly of the models that are not aligned as being dangerous and we shouldn't deploy them, there is probably very likely just one that we can't tell is maligned because we don't have well enough understanding, and then it looks good to us and we deploy it and then it kills us.